Hello everyone, and welcome to our webinar on managing erosion and sediment from forest roads and tracks. We'll cover the basics about the physical processes of erosion and sediment movement, and we'll look at the various measures at your disposal to control erosion and sediment movement. I recognise that you all have quite a lot of experience in the area, and I'll try not to teach you how to suck eggs, but at the end of the day, I do hope that you've got a better idea of how to comply with the Forest Practices Code. So why worry about track erosion? Well, first of all, we've got the very real risk to water quality and stream condition. I'm sure you're well aware of that. We also have, in your interest, the need to protect your investment, which is substantial, of the order of $5,000 to $25,000 per kilometre. And it's a lot cheaper to do it properly in the first place than to have to go back and get it right a second time and a third time. And then sitting under all of this, we have the obligations under the Code of Practice. So as we go through this presentation, I'm hoping that you will appreciate at the end how we can avoid these sorts of situations, all showing erosion and sediment movement off tracks and roads, the safety issues associated with it, and that you'll be in a position to have a situation such as this. We've got a forest road which is generating minimal sediment and is very serviceable for doing what it's supposed to do, which is to get you in and out of the forest. The resources that we use, and I hope that you will refer to, sitting over everything, we have the Forest Code of Practice, the Native Forestry Code of Practice, and you'll be familiar with that. We've got supporting publications and guides, which are also very useful. Sitting on the top of the pile, we have the New South Wales Rural Fire Service Fire Trail Design, Construction and Maintenance Manual, which in a lot of ways is the role gold standard for technical manuals. It's very practical. It gives you very clear and precise instructions on how to do what you need to do in the forest. We also have an earlier publication, perhaps the first attempt to put a manual together on managing unsealed roads. That's useful. And then we also have Forest Corp's Forest Code of Practices, which is perhaps a more beefed up version than the one that you operate with. It has quite a lot more pictures and diagrams and is designed to be a good practical working document. And sitting behind a lot of this work, we also have quite a body of research. A major project that I was involved in between 1995 and 1998 and carried out by the CRC for catchment hydrology measured in some detail erosion from forest roads and trails and the sediment delivery of that sediment to the drainage system. We had a special focus on the effectiveness of a range of management prescriptions, such as how rollover banks work, the effectiveness of filter strips, and what happens when runoff comes out of a culvert and runs off down a hill slope. It established a good, sound research basis for the management prescriptions that have been put together in the various codes of practice that have been developed since then. And if you'd like to read more, this publication at the bottom here is available on the web. So in simple terms, what causes a track to erode? The first part of the process is the removal of the vegetation and the topsoil, which provides a protective cover in the natural condition. Once the road starts getting used, we get compaction, we get wheel ruts, and we have an increased rate of runoff compared to the natural condition. This runoff then erodes the surface and carries sediment either from the surface or through drains and washes off the track and has the potential then to run into watercourses. So at the start of the system, we have the topsoil, and I'd just like to spend a minute or two in emphasising the importance of topsoil. In particular, you'll see here the infiltration capacity of topsoil is of the order of 100 millimetres an hour. That is, topsoil in its natural condition can absorb pretty much any storm that's thrown at it. It also has a very high storage capacity of the order of 60% or more. So whilst the topsoil is able to absorb much of the rainfall, it really then depends on how much it takes to saturate it, but this could well be at the order of 100 to 200 millimetres before the soil is saturated and generates runoff. So runoff is rare in the natural condition. If we scrape the topsoil off, we start getting down to layers which are far less absorbent and generate runoff far more quickly. So the subsurface layer that you see here, the silty loam subsurface, it generates runoff quite quickly because it will only absorb water at about 10 millimetres per hour, so 1/10 of the rate of the topsoil. And runoff is therefore going to be much more frequent. So we go down another layer in the soil to the clay subsoil, and often this is what we're building our roads and tracks on. We have a capacity, a permeability rate of about 10 millimetres per day, obviously very minimal. So basically a clay soil will generate runoff almost immediately. It really only takes a couple of millimetres of rain to generate runoff. Hence, the topsoil is doing the job of absorbing the rainfall and protecting the soil surface. We've got some modelled soil erosion rates on common forest soils. The yellow bars are a yellow granite soil. The red bars are a gravelly shale soil. So what we see here is the natural erosion rate, the figure at the top, the bar at the top, which you really can't see, it's so low, 0.02 tonnes per hectare per year. So this is on a soil with a protected topsoil and vegetation intact. We've basically got something of the order of 2 kilograms per hectare per year, which is nothing. If we then go to the second bar, and there it says 24.1, we've removed the vegetation, we've removed the sort of very upper layer, if you like, that has the plant roots in it. And so we've increased the erosion rate by a factor of 100. So the number there, 24 tonnes per hectare per year, is effectively about 1.5 to 2 millimetres of soil removed off the surface. Once we get down 15 centimetres depth, then the erosion rate is again doubled to 54.1 tonnes per hectare. And then if we increase slope, if we go up to a more moderate slope, around 15 to 20%, we again double the rate of erosion. So you can see also in terms of the soil differences, we've got our granite soil is typically a little bit more erodible than a shale soil. But again, we have the same trend in the shale soil as we've got in the granite soil. We've got a very low natural erosion rate, which increases by the order of about 100-fold when we take the vegetation and that protective layer of plant roots and leaf litter off. Here we've got a couple of shots of some of the different soils that you'll encounter, and you can appreciate the differences in the way they erode. You'll be familiar with the red shale soils, the gravelly soils, which are represented by this soil here on the right, and the red granite soils on the left here, soils which compact down well and which tend not to erode at a great rate. They're good, stable soils to work with. If we come down here, we've got examples of yellow granite soils, which are a lot more prone to erosion, more challenging, more difficult to manage. Often these soils occur lower down in the landscape, and you can see this soil on the right side is typical of a gully line or a drainage line. So this is a slide showing actual measured rates of both erosion, but also the sediment delivery away from a track and the absorption on the vegetated area beside the track. So let me explain just a bit more, just to give you the full picture. Down the right side, we've got a snig track. This is the darker grey area. We've got a cross bank, and we've measured the amount of sediment coming off that's being eroded off the snig track. And then we've looked at how it's been dispersed and attenuated, if you like, reduced as it runs across the vegetated verge. This is a harvest area, so there has been some log removal and some vegetation disturbance, but fairly minimal on the lighter grey area. And what's happening is that you can see we have quite a high rate of erosion from this storm, which was a 1 in 5 year storm event. We've got 11 tonnes per hectare for this event, which is quite substantial. But by the time it's been diverted out onto the forest area, it's reduced by the order of a factor of 10, just by virtue of water soaking into the ground. And then it's run another 5 to 10 metres to the bottom of our measuring plot. And really we see that a lot of the soil has been absorbed. Now this is a sandy granite soil, so the soil is erodible in the first place, but at the same time, once the water slows down as it runs off across the compartment area, a lot of the sand falls out as the water soaks in. On the left side, we've got a shale soil, which is less erodible, but the material that comes off the snig track is more clay, it's finer material, so it tends not to soak in, it tends not to drop out quite so quickly. So we've got the erosion off the snig track, the runoff diverts across the forest area, the forest floor, it soaks in, but not quite at the same rate as it does on the granite soil. But notice again though that the amount of sediment in the runoff has still been reduced by a factor of 10 once it runs off the track and out onto the forest area. So I've introduced you to the erosion process, the difference between some of the soil types. Now, what happens when that water, the runoff water carrying the soil, runs towards streams? We'll introduce the concept of connectivity, which is really something that you as operators can have quite a big impact on. So look at the diagram here. We'll start from left to right. We've got a situation here where we've got a diversion bank or a culvert directing runoff out onto the hill slope. The hill slope has a divergent form, that is, it spreads out the runoff, and so water has the opportunity, the runoff water has the opportunity to soak in, and therefore it doesn't run very far. It basically soaks in within a matter of 20 or 30 metres of the outlet. Now we've measured that as part of our research project, and we found that at the sites that we were dealing with, for every 10 metres the water runs through the across the forest floor, we get around 30 to 40% of the sediment dropping out, simply because the water has the opportunity to soak in. So that's something that you can work with in order to locate your drain outlets if you want to maximise the capacity to infiltrate and control the sediment movement. We have other situations where here in this particular site, we have a partial linkage, if you like, where the landform is such that there is a certain amount of convergence. So the runoff goes further down towards the stream, but in doing that, it's still soaking in. So there is more, if you like, concentration of flow, so it's going to go further before it actually soaks in. Coming across to the right side here, we see this heading full channel linkage. Now, this is a situation we see sometimes where culverts are blown out and they've created a gully themselves. They've created a channel where the water follows all the way down to a drainage line. That obviously is something to be avoided because there's very little opportunity for sediment to drop out if the runoff remains concentrated and channelized. That's a location where perhaps you would move that culvert outlet to another spot where it has the opportunity to spread out. Now, two other sites which you'll be familiar with are where roads actually connect with the drainage system at perhaps a ford, a low-level crossing, or a bridge on a more major stream. These are situations where considerable effort is needed, first of all, to make sure the structure is safe, but at the same time, there are also conditions in the code to try and minimise the amount of sediment running down the road and connecting with the stream. And the particular condition requires that you have a structure to direct runoff off the road somewhere between 5 and 30 metres from the drainage feature. Okay, so the key points in the process that we're trying to manage: the track surface itself generates runoff even after a few millimetres of rainfall, and that runoff creates sediment by the erosion process. A bare track surface has a high erosion potential compared to the natural forest floor. Additionally, the traffic use tends to break up the surface and create easily erodible soil particles. And this has been shown in the research. Roads which have a high usage get broken up to a high degree. Roads which have minimal usage, such as access roads into forest compartments, that sort of thing, that end up with little use after they've been built, they generate considerably less sediment. Once that sediment-laden runoff leaves the road, it runs across a hill slope and either directly or indirectly can access the watercourse. So I've distilled a couple of key principles, and at the end of the day, we'll have 4 key principles, 2 of which are here. So the first one is to keep disturbance to a minimum, because keeping the topsoil intact will basically minimise the erosion that we have to deal with. But it relates to the second principle. We want that topsoil to be intact because that's what we want to do the absorbing of the sediment-laden runoff. So keep those principles in mind. Disturbance minimised, and what we want to do is maximise the potential for runoff to be absorbed on the forest floor. Okay, planning. So just changing tack here, we're going to talk about really something that is absolutely crucial if we want to avoid track erosion as much as possible. We need you to be basically familiar with the site over which you're building the road, and we need to carry out perhaps a more formal planning process to make that happen. So first of all, the first step is to appreciate fully the purpose of the track. Is it going to be a permanent road or just a temporary road to be open while the logging operation's proceeding? What sort of volume of traffic will it take, and what type of traffic? Will it be log trucks fully laden, or is it just going to be occasional 4-wheel drive usage? The next step is to carry out a more detailed site assessment. This can be done in the first instance using maps and air photos, but it also needs you to get out and have a good close look at where a road's going to be built. Or in fact, even just for snig tracks, you need to be familiar with the site before you actually drop the blade. The sort of things that you need to look at are signs of where you might have erodible soils, so soil erosion hazards, where you'll be putting in drainage line crossings. You'll have a map which has your drainage lines marked on it, your first order and second order streams. You also need to note where you've got depressions, areas which will carry water, which will get saturated, and which could cause a problem if you need to go through them. Any landform issues where you have very rocky ground, where you have your poorly drained areas, and then also steep slopes. The steep slopes particularly are a problem because as slope increases, the amount of cut and fill increase, and this increases the erosion hazard and also the landslip hazard. And then at the end of all of this process, you'll have the ability to identify the route that you want to take for the road, and you need to show that on your forest operation plan. So a few tools that are very handy to do all of these steps. First of all, the 1 to 25,000 topographic maps and the 6 maps imagery, which you can access online. Both this map and the imagery have come from 6 maps, and you can see on the topographic map that it has the streams, and you need to do your stream ordering off the topographic map, so it's useful for taking that step. It also shows where the previous existing tracks are from previous logging operation, so that's going to be useful in planning up whether you need to carry out construct new roads or whether you'll be able to use existing roads. And the contouring gives you a good idea of where the ridges are, so where to locate the track to minimise creek crossings and drainage line crossings. We have a few other resources which I'm sure you're familiar with. Google imagery sometimes is very useful because it has a much better resolution than what's on the 6 maps imagery. And soil landscape maps can be quite useful too. You can access soil landscape information at this website, and that will tell you, for instance, where your granite soils are, where shale soils are, and you can relate soils that you know which have perhaps a high stability and are good to build a road on compared to other sites which are less stable and more problematic. Okay, so our third principle, and I think this is a fairly fundamental one, is to plan before you push. Keep that in mind. Okay, so the various tools that you have at your hand to manage track erosion really come down to a range of measures, but in a lot of ways it boils down to drainage, track drainage being the basis of a lot of these measures. I'll put them into boxes here just to sort of categorize them a bit and structure the next part of the presentation. And we can see that we will have track surface drainage here, and that comes down to a range of measures including crowning, infall, outfall, and table drains. Relief drainage is about relieving the pressure in the drain, or the pressure created by runoff running down the road. So this is where you're getting water off the road surface and out onto the hill slope. We have cross banks, mitre drains, and culverts to do that. We then get onto drainage line crossings, and we've broken that up into major crossings and depressions. And then a couple of other matters which are really about protecting the edges of the road, the batters, and we'll just have a look at cut and fill batters and topsoil management. But here's the basic principle, in a way, of all of these measures. It's all about getting the water off the road safely. So surface drainage, the first measure is broadly termed crowning. So this relates to a constructed road where fill has been imported and you're able to build up the road such that it will shed water to either side. You get water off the running surface in that way and drain to the table drain on either side, and the table drain does the work then of transporting the water to where you need it to be disposed. Infall drainage is perhaps not the most common form of drainage, but is crucial where you have a substantial fill batter on the outside. So it's going to be a particular drainage measure on steeper slopes where, in cutting the road in, you've generated a lot of fill. So we've got this outer area here which is built of fill, and we don't want the runoff from the road surface to drain over the edge there. We want it to run inside into the inside batter and then into a table drain which will take it away to a safe disposal point. The opposite of infall drainage is outfall drainage. Perhaps this is the simplest, and I think probably what we would encourage to be applied in as many cases as possible. The situation where you would apply outfall drainage is where you have a fairly minimal fill batter for a start, over which the runoff will drain. But basically what we're trying to do is to get the water off the road as soon as possible. So we want the water to drain across rather than run down. And by creating outfall drainage, we can do this with basically a minimum fuss. You can see there's no need for a table drain on the inside, that the water will drain over the edge and onto the forest floor. On a more major road, a built road, we have table drains, and you can see here we've got the drain running either side, carrying the runoff that's been shed from the centre of the road, from the built up area of the road. The water runs beside our track surface and then collects at some point and is directed off the road and out onto the forest floor. In this case, you can see we've got a diversion bank, but in some cases that will be a culvert or a mitre drain. And in this case, on the left side, you can see water runs down the table drain here to a point at the end of the cut batter and is able to drain out onto the forest just with a mitre drain. The issue with table drains is, though, they very often tend to scour out, particularly on soils which are problematic. Here we've got a sandy granite soil. But in this case here, you'll see that we've fixed a problem created by a table drain, which by virtue of the lie of the land, it was unable to get relief drainage through a culvert. So we've had to carry the water well down the table drain before it can be relieved. In doing that, it's scoured out. So we've used rock to reinforce the table drain and protect the surface. A case like this on the right side, typically the problem occurs because of inadequate relief drainage. So basically the water is running too far down the table drain before it can get out. Now these distances are specified in the code and they're aimed at providing protection to the table drain by relieving the load in enough situations so that it doesn't cause scouring. There may be situations, however, which when you're dealing with difficult soils, you just need to provide a protection of the table drain, and this can be done with either imported rock and gravel or with jute mesh and allowing the vegetation to grow. Diversion banks, probably the simplest and probably the most effective way of draining, of providing relief drainage. Probably they're going to be more used on unformed, informal roads rather than a major road. But the aim of a diversion bank, sometimes called a rollover bank, sometimes called a woo boy, is to pick up the runoff and direct it out onto the undisturbed ground surface. On a larger road, they're going to be built to a grade and a size where they're easy to drive over. And I guess the issue is that because you're using soil from the road to build them, that if you start getting up onto steeper slopes, it becomes very difficult to get the size in the bank without over steepening the downside. And so we say that the maximum suitable grade for a diversion bank to work effectively is 20%. Now, keep in mind the diversion bank is not a sediment control structure. It's a diversion bank. It's aimed to get the water off the track and out onto the stable forest floor. So you have a big effect on how this is going to happen just by where you site the diversion bank. You really do need to put some thought into being able to ensure that the water coming off the road will spread out and isn't going directly into a drainage line or a depression and doesn't have the chance to spread out. So that's one area where you can have a big effect on how effective the erosion and sediment control is. Here we've got a side view of a well-constructed bank. Obviously the vehicle can drive over, a log truck would be able to drive over something like that. Obviously this one on the right just doesn't have enough volume. It's overtopped and is, to all intents and purposes, doing nothing. In the Code of Practice, there's specified distances for the spacing of cross banks, of diversion banks. This table comes from the RFS fire trail management manual. It's a little bit more detailed than the one in your code, but it still provides the same basic guidance and gives the same idea that as road grade increases, as steepness increases, and the energy to erode the surface increases, we need to have more frequent rollover banks. So you see here, less than 14% grade, we have spacings between 70 and 90 meters. As grade goes up in this column here, we have spacings becoming more frequent. So there's a certain amount of flexibility in this spacing, and that's to allow you to choose the best spot to locate the outlet of the bank. So to say a specified distance that the banks have to be apart defeats the purpose of actually having the best spot for the outlet. So there's a certain amount of flexibility to ensure the most effective diversion of water off the track and out onto the forest floor. So we've got a video that gives quite specific instruction on how to build a good crossbank, how to site a crossbank, and then some of the finer points in actually building a bank. You can access the video at this address. It's only 8 minutes long and is designed to be very practical. So if you've got time, have a look at that. So another form of drainage are mitre drains. Sometimes you'll call them push-outs. These are situations where, these are suitable in situations where the landscape allows you to get the water out and basically will just disperse out into the vegetation. The key part, you'll see that they're angled around to take the grade out of the flow, so it's not running quite so fast. And as it comes around, it then is directed out onto the forest floor where the runoff can spread out. It's not a bad idea to try and open out the end of the mitre so that the runoff starts spreading out before it gets to the end of the drain. But perhaps the key thing is where you're directing that water to. The first thing is to make sure that the hill slope isn't such that it will just run back to the road. The runoff needs to be going away from the road. So if this is the issue, if it's going to run back, then we really need another form of relief drainage, possibly a culvert. And then the other issue is we don't want the runoff running out over areas that are disturbed or not going to absorb runoff. We want the runoff to be soaking in. Culverts, we see culverts in many situations, both good and bad. Culverts are there to convey water under the road where it's running along an inside and we want to get it to the outside to drain out onto the hill slope. Sometimes they may also be located in small watercourses to convey a watercourse under a track. There's two parts to the culvert. One is the pipes, obviously, but the other important part is the head wall, and the head wall is crucial. There's no point in putting a pipe in unless you actually put in a head wall, because the soil, the fill that goes over the top of it will just fall in, find its way into the watercourse and become part of the problem. Additionally, because the water is coming out of a concentrated flow, it's often worthwhile to put in protection. And you can see here we've got a rock apron protection of the culvert outlet to protect the drainage depression and to make sure it doesn't start washing out. So in constructing a effective culvert, we really need to be concerned with pipe size. There's no point in just putting a pipe in of any old size. It's going to clog up with debris and is only going to cause a bigger problem than what you're trying to fix. So you can see here that we've got a culvert that was under designed and has clogged up, and then we've got runoff going over the road surface when we really need it to be going underneath. And we've got a situation in this photo where culvert pipes were used for a reasonably major drainage line, and they've obviously blown out. So to solve that problem, we move on to drainage line crossings. A word of warning first, that if you're crossing third order streams or higher, that you'll need to get a controlled activity approval from the government, the relevant government agency. First and second order crossings do not require controlled activity permit, and also drainage depressions which are unmapped. For larger features, for larger crossings, engineering design is recommended, and I would suggest that that is applicable, if not on first order, on second order streams, and also where you have substantial banks, a substantial channel to deal with. Engineering design is crucial. So the aim of a drainage line crossing is really to create as little disturbance as possible to the bed and the banks of the channel, to allow the channel to do its work, to convey water and not have the flow obstructed or diverted in any way. And this diagram, it's a bit of an idealistic sort of diagram, but it shows the principles that we need to apply. The first is the idea of getting the runoff from the road off the road before the actual crossing. The code specifies at the very minimum 5 metres and at the very maximum 30 metres from the drainage line. So you can see we've got a crossbank here directing road runoff off into the forest floor, and with the opportunity for it then to infiltrate before it gets to the drainage line. Then we have the approaches and the actual flow lines reinforced with rock. And so this part of the crossing is protected, it's armoured, and at the same time in the crossing there's no obstruction to the flow coming down the flow line. So you'll see that we're really trying to encourage in all drainage features, both minor and major, the idea of bed level crossings. We're trying to get away from culverts. These are just minor crossings where it's a problem with occasional flows. You'll see that this one here has been constructed by dropping rock and compacting it. This one's a concrete ford, probably not the sort of thing you're going to build, but there may be some situations where concrete is justified because of it's expensive. But if it's going to receive a lot of use and it's a particularly boggy spot, it may well be worthwhile. When we move to larger drainage features, obviously it's a more major and more costly operation. There's going to be perhaps a little bit of shaping up of the banks to get the right angle. But you can see here again, we've got an approach with a rock armoured run in and out, and then the water flows run across the reinforced bed. So that crossing is usable, perhaps not in a flood, obviously, but in most conditions, even though the water is, the creek is carrying water. This is just a short sequence to show you what's involved in building a crossing like this. They're not a small undertaking. This is on our top left side, we've got the original condition of the crossing. You can see it's a hell of a bog and isn't going to be serviceable as soon as it's wet. And to use that when it is wet would be in breach of the code. So what we need is to be able to provide a stable approach and also a non-obstructive feature in the channel itself. The crossing, the actual road is deepened, is actually pushed out, and we need to lay geofabric on the base of the road. This is to stop the rock sinking and basically becoming unserviceable with usage. This maximises the longevity of the crossing and will allow it to be used for larger vehicles as well. And this is the finished product. You can see that it's stable from the top of the banks down through the channel and up the other side. Road drainage at crossings is a crucial part of the Code of Practice and is crucial to prevent sediment getting into watercourses. The basic requirement is that runoff water is taken off the road surface somewhere between 5 and 30 metres from the crossing and is disposed of safely onto the hill slope. And you can see from this picture, we've got a drainage crossing here, and we've got a diversion bank back here, perhaps 15-20 metres from the crossing, pushing water that's coming down the track out onto the forest floor so that it drains down here and takes a a pathway through the forest where there's a much better chance that the sediment will be absorbed as the water infiltrates. Batter stabilisation is often a crucial part of road construction, and particularly when we're on steeper slopes. Some situations, such as this top slide show, will just naturally revegetate where the batters can be laid back and where the soil is reasonably amenable to grass growing and vegetation re-establishing. But there will be many situations where additional works are needed to be carried out. And I guess what you really need to take into account when you're planning these situations is that building a road on steep slopes is going to be an expensive proposition to make sure it's stable and to comply with the conditions in the Code of Practice. So the key issues are that you need to have a batter grade if you want to be able to grow grass on it, to stabilise it of around 2:1 to hold topsoil and allow that grass to grow. It may be possible that, especially on steeper land where the cut batter is into rock and you don't, it's not practical to try and stabilise it by growing grass on it. But the main issue really that you have to contend with is drainage on the fill batter, because that's where a lot of the instability will come from. So you can see a diagram here showing the need for some sort of batter protection where the culvert or the relief drainage directs the runoff. It could be a diversion bank, it could be a spoon drain pushing the water out over the batter, and then where that water runs down to natural ground must be protected. It's just not possible to drop that water down the batter without causing erosion if it isn't protected. So here's an example from State Forest, New South Wales forests on the north coast, where obviously this culvert is quite unacceptable. It's just shooting water out over the batter. You can see that there's also water running off the road itself. And really, as well as causing a major erosion and sediment export issue, the road's just not safe. The road's not stable. And there's an issue that a risk that this will collapse as well. Let me just go back and reiterate a point here that your code requires that any tracks across steep slopes taken to be over 25 degrees must have geotechnical design, as the batters have a high risk of erosion and slumping. So this is one option. It's not the only option, but it's one way of taking water from a culvert outlet, running it down a batter and onto rock protection of a channel, and allowing it to run away onto the forest floor. When you're building a road, you'll be scraping off topsoil, and it's a pity just to see that topsoil wasted in a windrow or a pile or in a batter. So give some thought to managing the topsoil so that you can reuse it to help maintain the stability of the batters. So with a bit of thought, you'll be able to find a location where you can stockpile the topsoil, and then you're in a position to be able to reuse it once you've finished, rather than seeing it covered up in fill as it comes out of the cutting. So it's something to perhaps think about, actually having a formal location of where you might stockpile your topsoil, somewhere that's going to be out of the way of the main construction activities. And then when you can access it when you're finished, to respread on the batters We recommend a maximum topsoil depth of 15 centimetres. Once we start getting deeper than that, we start to risk it slumping off the batter. And look, finally, the issue with tracks is maintenance. I think people often think that they can build a track and then forget about it. It's really not set and forget. Maintenance is required, particularly to protect your asset. You really do want to look after it and try and minimise the risk of problems caused by runoff not going where you want it to go. And in this case particularly, you can see that we've got a culvert that's filled up with sediment after a storm, and any more water running down here is just going to wash out the road. So really, we would suggest that after major storms, maybe it's a wet weather activity when you can't do you can't access a forest, is to do some maintenance, clean out culverts, clean out diversion drains. The risk with diversion drains is, of course, that they'll overtop and then runoff will continue down the road or down the track. So there's certainly a need to keep up the maintenance on a regular basis. We would say, if not after storms, then at least on a once every 2 years. Okay, so the 4 key principles that I'd like you to take away, and I think encapsulate pretty much everything we've been talking about, are to keep disturbance to the minimum possible, therefore reducing your risk of erosion in the first place. To plan before you push, get to know the area that you're working with, work out the route of the road, taking into account where the ridges are, where the drainage lines are, where the risky sites are, putting it on a map, and then you can have a record that's part of the plan of operations, part of your formal plan then. Drainage practices, all the different forms of drainage that we're talking about, are all about getting the water off the road safely. So all those various practices, mitre drains, culverts, drainage diversion banks, are all about getting water off the road and trying to minimise the opportunity the water has to cause erosion. And then once the water is off the road, the sediment-laden water is running out over the forest compartment, we want to maximise the potential for absorption. And so we're looking really at you to identify the sites where water will spread out rather than concentrate, and where it has the opportunity to infiltrate, and therefore to prevent that sediment getting down into the watercourses. Okay, let's have a look at some practical examples, perhaps points for discussion later. We'll start off with some what I would consider good practice. We've got a snig track here on a steep site. The disturbance has been fairly limited, so you can see that really it's just the width of the dozer blade. There's minimal box cut, so the blade really has only taken off perhaps 10 centimetres of soil, if that. The track has cross fall, so water isn't going to be running all the way down the track, but when it does, we've got banks that have been built and they're doing their job. They're getting the water off the track. The spacing complies with the conditions in the Code of Practice. So you can see that the track is in pretty stable condition, and we don't have all the signs of erosion that perhaps we'd see on a less effectively installed track. Good practice. This again is what we call our bed level crossings. So we've got rock reinforcing of the bed and the approaches. We've got no obstruction of flow, and We don't have the problem where with culverts you have soil piled over the top and the problem of water dropping off the edge of a culvert and washing out the fill batters. Likewise, on this drainage crossing, these drainage crossings, you can see that we've got a reinforced channel part of the crossing here and here. And then we've got banks located between 5 and 30 metres from the crossing to direct runoff coming down the track. So you can see here runoff coming down this way is directed by the bank off down the hill slope rather than going directly into the drainage line. So the good things here, we've got track drainage in place. We've got good disposal points, so the water spreads out rather than running straight into the drainage line. And the crossing itself is protected with graded rock. This is also, I think, probably one of the key things that provides good protection of a forest harvesting operation is the use of walkover harvesting techniques and therefore minimal disturbance of the soil and keeping the protective vegetation in place as much as possible. So you can see there's very little opportunity for runoff to be concentrated down wheel ruts and the like. And we've also got good crossfall drainage. So looking at these photographs here, you can see that there's really minimal opportunity for erosion in the first place, and then for runoff to be following down a track and creating a further issue of sediment. So that's a desirable, what I would consider a desirable type of log harvesting operation. Now, in contrast, we have a situation where we have excessive disturbance. We've got a couple of SNIG tracks here, where I would suspect probably there's been very little consideration to how we're going to get the logs out. This, I'm sure, could have been avoided basically by either walking around the compartment and working out the route in and out. But what's happened is we've got a little bit constrained by trees down the way, and so we've had to change direction. But in the process, the blade's been down, so disturbed a very large area of soil that really did not need to be disturbed. And likewise here, in this case here, presumably this is track construction, but we've disturbed a hell of a lot more area than is required for the actual route. An example of unacceptable drainage crossings, you can see that we've built up some fill, put a culvert on, put a pipe in, and then we've tried to put some sort of barrier here to retain the road surface in place. But really what we've done is created many cubic meters of soil which has the potential to wash directly into the drainage feature. So this is unacceptable practice, and really it's the sort of situation that would be best addressed with a bed level crossing with imported rock. And that will create a situation that allows, if not all weather access, certainly access when otherwise it wouldn't be possible with the creek running and the like. Okay, I think everybody knows this issue. We've got a windrow running down the outside of the track here, so the possibility of water being directed out onto the forest compartment is being prevented, and so runoff will run all the way down the track. It's really quite a simple matter to keep windrows at the absolute minimum. Sometimes they're required for sure to protect a fill batter, but we're really need to just take the effort to spread this out and try and ensure that runoff can drain from the track as easily as possible. Steep slopes. Look, really, this just reinforces the fact that if you are putting in a road on steep slopes, it's going to be a major operation. It requires a lot of planning. On slopes this steep, obviously well over 25 degrees, it needs geotechnical design, and it's going to be expensive. We need to have protection of both cut and fill batters, constructed drainage to handle any small catchments running across the road. But you can see here in a poorly done job, the risk of erosion, the risk of slumping is huge, and the risk to pollution in the watercourse is it's almost a foregone conclusion. Okay, so just going back, hopefully you'll remember the 4 principles that we covered, that you'll have an understanding of some of the basic processes, erosion and sediment delivery, where you can have a role, particularly in controlling how they occur. And then you've got your toolbox of techniques in terms of how you'll carry out road drainage. So from here, we'll move to a question and answer session. Thank you.